So, hi everyone. So today I'll be presenting this paper. CLEEP is also an efficient segmenter, which is published in the CVPR. So these are the main contribution of this paper. This paper is a weakly supervised semantic segmentation method, which is current state of the art. And in this paper, they presented a different loss function, which performs better than the existing loss functions of previous state of the arts. And they introduce class-aware attention-based affinity module to refine the initial CAM, which I'll go in more details with what is CAM and others, and put to segment the images in weakly supervised fashion, and which also solves the confusion problems. Yeah, and this method is also like 10 times faster than the previous existing methods to generate pseudomask. Before going to that paper, I'll briefly cover this paper, the CLEEP original paper, which is in this paper, because this method is heavily used in current paper and previous paper also, which Alkan presented. So this is the brief overview of CLEEP. So here we have two encoders. One is text encoder, one is image encoder. And in image encoder, we have some image inputs, and in the text encoder, we have corresponding text input. And then they try to create a matrix where they take the dot product of text encoder, encoder. Yeah. 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 So they take the encoded text and the encoded image and take the dot product of both and create the matrix like this. So one thing to notice here is like this diagonal axis is the axis where we have the correct label and the correct image, because here we have I1 and T1. T1 is the text input for image 1, T2 is the text input for image 2, and so on. So CLEEP is trained in a way that we maximize this portion of the matrix. So they transform it into a probability using softmax. So we train CLEEP in a way where this portion of the matrix, the diagonal of the matrix, maximizes. So in this row, this element will be the maximum in this column. This element will be the maximum, and so on for the other columns and the elements. So what happens when we train CLEEP in this fashion? So when we start our training, our text encoder, which is already pre-trained, and image encoder, which is also pre-trained, but when in the beginning, both image encoder and text encoder do not have the information of the text related to the image or the image related to the text. When we train the model in this fashion, the image encoder gets the knowledge, some sort of information of text related to that image, and text encoder also gets some information of image which is related to that particular text. So they create some correlation between image and text in text encoder and image encoder, vice versa.
So actually, the text encoder, their features are becoming similar to image encoder's feature.
Yeah.
If text and images are matching.
Yeah.
And so, I mean, yeah, if text is properly explaining the images, then their features from text and image encoders are becoming similar by using this kind of laws.
Yeah. So, like, the size of this matrix depends on the.
This is done by OpenAI.
Yes, OpenAI. OpenAI is from Delhi. The Delhi paper and this paper were published in the same time, but the Delhi got popularity. It didn't get the popularity that much.
Yeah.
Yeah.
But it can generate monthly.
Yeah, yeah.
But this can do some magic.
Yeah, yeah.
Not fancy.
Yeah. Yeah. So,
And maybe the right side is the thing which can be done by this clean model, right? The zero shot.
Yeah, it's a zero shot learning. Yeah, I'll get there. So the size of this matrix depends on the mini batch size, and according to that, according to the authors, they say if the mini batch size is large enough, this model can explain all the context of the world. So what it means is this model is trying to comprehend between text and image, so scene and the corresponding text together. So if the batch size is large enough, it can learn how to differentiate between text and image in large scale. So it will be more generalized. And another interesting thing of this paper is once the model is trained, we do not need to train it for the separate task. Let's say we want to differentiate between cats and dogs or human and anything else. We don't have to train the model for one particular task. The model is generalized enough to perform well for any task. So this is the one example. After training this model, they were trying to classify a dog. They gave some inputs and tried to classify, and the same model gave the proper response. Yeah, this was the brief overview of CLIP. And this,
So
yeah,
this is very important.
Yeah.
So maybe for image classification,
Yeah.
if we use the ResNet or other image classification network, we have to our output probability will come from the softmax layer, right?
Yeah.
But here, what they do is they extract image encoder feature, and they extract some text encoder feature from some word. Like that word becomes the class actually. Like dog or bird, plane, right?
Yeah.
So we can add new class in that word, right? And extract some text encoder feature from that class name and match which one is best matched to the image encoder feature. Right? Then we can judge if the dog class, their feature, text feature is closely matched to the image encoder feature, then we can conclude that that image contains dog. Right? So in this way, we can do zero shot.
Yeah.
So we don't have to train with some predefined class, but we can classify images into some new class in this way.
Yeah.
It does mean that we have to compare to all the world in the test embedding space. So, but if we do it, doesn't mean we have to compare the embedding of the image to all the embedding of the world in the test.
Yeah, we have to compare with all the world, all the candidate world. But that's not the big issue. But
Yeah, once it's trained, you can just infer it. So in inference, it doesn't take, it takes long, but it's not as heavy as training. And you don't have to train it for separate tasks. So once the model is trained properly, that model is generalized for classifying the text and
More than 10,000 animals in the world like that.
Yeah.
You have to compare with all.
Compare with all of them. Like when training, it should be trained on large data set.
And
yeah, but once we will talking about the training.
Yeah.
We can't train that.
Yeah.
Yeah, in the training, we are training that model using millions of words.
Yes.
So the testing, we have to compare with 10 words, as you mentioned. Yeah.
Yeah. And that model is trained by OpenAI, so they have the resource. Yeah.
They publicize the pre-trained model.
Yeah.
We can
So
use that.
we can use that trained model.
Testing, we have to anyway compare with all the candidate words.
Yeah. Yeah.
And thirdly, one idea for Roman and what Roman and Puja is doing the star galaxy classification. Maybe we can try that. high galaxy classification and also the for that kind of thing. But that is not dedicated. Actually, this is not developed yet for the object detection. So maybe not yet. But anyway, that could be something that I need to future. Let's go.
Yeah. Okay. So this is basically what I've described so far. So this paper is a weakly supervised semantic segmentation method. So what is weakly supervised segmentation? So in semantic segmentation, in supervised learning framework, we require pixel-to-pixel annotated data. So like we annotated in our data set, we require pixel-to-pixel data, but those kind of data sets are really hard to get. So in weakly supervised learning, we can use image level labels. So let's say one image is classified as cat, one image is classified as dog. We can use those images and train our model to get the segmentation or the bounding boxes or the points or the scribbles for weak supervision, which is much more accessible than pixel-to-pixel annotated data. So a weakly supervised segmentation method has 3 stages. First stage, they are trained on a data set to generate initial camps, which is called the class activation maps. And then they use pixel affinity network or extra saliency map to refine the initial cam, and then they create pseudomask using the refined cams. So what is cam? Cam is basically a method where it tries to visualize the specific area of an image which is responsible to make a decision for a model. So here, this area, so for person, this area is responsible to classify as a function. So this is the cam for that particular image for person class. Here, this is both, and this area here responsible for classifying this image as a both image. So this area is cam for that particular image for that particular class. And grad cam is basically they use a gradient of the model to visualize this specific area. So this is the overview of the method. So here, I'll go to the scan M part later. Here, what they basically say in clip, we have seen here, they're not exactly saying dog or car or plane, a photo of a dog or a photo of a car or something. So they need to have some background information of it. So they cannot exactly say a specific object or specific thing in clip to describe it. You need a bit more detailed explanation of that object. So here they say they add some categories of backgrounds to get better segmentation, so which is described further later. So again, they encode the text with some method, like they try to prompt engineering some text input. They get the text encoded text, and also get the encoded image. They get the probability we have seen earlier, and then they use that probability to get the first initial mask, and then they use the transformers multi-head self-attention, and the new proposed class-aware attention-based affinity together to refine that initial cam. To get the refined cam, then they use DCRF, which is a method to get pseudomask from this cam, and they use the pseudomask to get the segmentation. And then in the last, they introduce some loss function using the confidence map to train the whole architecture. This part, basically this part, they don't train the clipboard is fixed. So just to train this bird, they came up with this confidence map, and trained it, and found better results using this confidence map. So let's
using pre-trained model, using pre-trained clean text encoder and pre-trained image encoder, they can somehow generate the segmentation mask. For the given image. And for any object, any new object. And then they will train that training new model using those as the new data.
They train this part on Coco dataset and Pascal dataset, Pascal VOC dataset.
And actually, GraphCam, that is one separate paper. Actually. So GraphCam was proposed to, for example, for image classification network, if their class is dog, they can activate where to see actually without explicit training. So GraphCam is doing that, but here they extend GraphCam for click the text and image pairs. And then using that, they somehow zero-shot manner, they can draw some canned result using using testing. I think that's no good idea here. But we don't need any training in the left part. So using pre-trained network, we can anyway generate some pseudo graphs for the segmentation. And using that, we train new segments. The idea is quite interesting.
Maybe
following this.
Maybe we can extend it also to object detection, because if it's doing
detection is more easier.
If you're doing weakly supervised segmentation.
WSS and WSOD, that's weakly supervised object detection, is called as WSOD. And those are already in those fields. There's a lot of papers. But normally people think WSOD is easier than WSS. Because if we do WSS, if we can get that defined then bounding box could be obtained already. So WSOD is in that sense easier for them.
So in their method, they're shown the way of using GradCam and softmax function together. This is they don't need training, as Professor said earlier, and they introduce basically prompt engineering. So they introduced two methods: sharpness-based prompt selection and synonym fission, two methods to select prompts for weakly supervised semantic segmentation. And they also presented class-aware attention-based affinity and confidence-guided loss, as I've said earlier. So let's go a bit in details into this. So this softmax GradCam. So this is also can be better explained here. So here, when you are saying a photo of dog, so in this part of the vector is going to be maximized. So, and the rest of these rest of the elements of the vector for this image are gonna be less than this element, but this property is good for image classification. But when you go into segmentation, there can be multiple classes which can be the target class for semantic segmentation. So let's say there are a person and a boat together in the image. So there are two classes. So in this way, we cannot get two classes with the maximum probability. So this is a problem of this method. using segmentation. So they say, like, if we do the prompt engineering properly, we can get away with this problem, but just from the loss function or something, it's really hard to get away of getting multiple target classes being maximized in the output of a clip. So these two slides, basically, I tried to write down what I have explained so far. So how did they use text-based prompt? So for the prompt, the first method they introduced is sharp-based prompt selection. So for calculating sharpness, they used this equation where here, this one is for the variance of target classes, confidence in all dataset, in whole dataset, and the mean of confidence of one particular class in whole dataset for one particular prompt. So the less the variance is, the better the prompt is. So in their experiment, they found out some abstract description like origami or rendering performs well in segmentation tasks. Also, some adjectives like clean, large, and weird have a positive impact on segmentation performance. So they tried to do some experiment on Pascal dataset, and they found out this prompt gave them the best accuracy in terms best performance compared to all the other prompts that they've tried. They gave the lowest sharpness. Lowest sharpness means the lowest variance in the confidence. So that's why they've chosen this one to go forward with. And they also found out if we use the, so for synonym fusion, they have found out if we use the synonym of one particular object, the clip gives better result. So let's say when you're using a clean origami of person, people, and human, it masks whole human. So, but when we just say a origami of person, the clip, the whole architecture tries to select just face part. That can be happening because in the training of clip, the person and the could have been just trained as the face, and the rest of the part of human body is classified as clothes or something. That's the reason the authors think is. So to mitigate the problem, they say just use the synonym of same particular object together when you're giving a prompt. Classware attention affinity. So to refine the initial CAM we have gotten from the previous steps, the existing architecture normally used the multi-head self-attention from transformer. But the problem with that thing is in multi-head self-attention, that is class agnostic. So, but the CAM is class specific. So the CAM depends on particular class, but self-attention head doesn't depend on any class. So when you use a multi-head self-attention to refine the CAM, we create the noise. We create noises in the CAM, which creates problem, which in the later part of generation pseudomask. So they came up with method, which is explained here, which is they use this affinity to get the refined map. So here PC is the box mask obtained from the CAM. So we can get the box mask from the CAM, like as Professor also was saying earlier. And for as I've said earlier, so CAM is class specified, and the self-head attention, multi-head attention, self-attention is not class specified. So we can get the class information is from MC and CAM map for the target class, and use them together to get the ultimate affinity to get the refined CAM. So, and here A is basically the self-attention, and they use sync-horn method, something I'm not sure about that method though, but they use that thing to get the matrix. And this is the conference catalog. So in previous methods in this part, once the segmentation models outputs the semantic segmentation, they used to use the whole image from the refined CAM to create the loss function. But here, but one other problem is in refined CAM, not all pixels are equally important for the output. So they created a loss function where it takes into it considers this brighter pixel as a more important pixel, and less bright pixels is as less important for the final semantic segmentation, and calculates the loss for that semantic one particular semantic loss forward pass, and calculate do the backpropagation. So this one is they get the confidence. So from the this is X is the CAM, and get the confidence of each class for each pixel, and get the confidence, and using that confidence they calculate the loss function if the confidence is above certain threshold. So this is how they implemented their whole architecture. They use Vision transformer of this version of Vision transformer, and they use DenseCRF to further process the refined CAM for pseudo mask input, and for final segmentation they use ResNet 101 based model from this place, and they also evaluated their model on Pascal VOC, this dataset, and Coco dataset. So this is the experiment result of this method. So the current state of the art for weakly supervised semantic segmentation in both Pascal dataset and Coco dataset. So here we can see it's the highest, and yeah, it's the highest here too. And this is the inference time. And in previous methods, they used to take around 6 hours the least, and now they're taking 0.6 hours to infer to create the semantic segmentation mask. And this is this much memory they were taking. Previously, they used to take 18 gigs, but they take just 2 gigs for their models. I guess it's excluding clip part. Yeah, because clip is big. I think it's excluding clip. So that was it for me. Thank you for listening.